Welcome, everyone. Please settle down. As you can see from our outline, today's session is dedicated to mastering the cracking of hydrocarbons to manufacture alkenes and hydrogen. This organic chemistry topic frequently appears in both your Paper 1 and Paper 2 exams. First, we will review the learning outcome, which is describe the manufacture of alkenes and hydrogen by cracking hydrocarbons. Second, we will tackle practice questions. Finally, we will analyze an organic chemistry question from the 2025 GCE O-Level Chemistry past paper. By the end of this session, you'll be able to describe this process, known as catalytic cracking, essential for matching the global demand for smaller hydrocarbon fractions. Let's get started. Open your notes to hydrocarbons and let's learn the cracking of hydrocarbons process to manufacture alkenes and hydrogen. Let's first look at where we get our starting materials. Where do we begin? Our starting materials are long-chain alkanes extracted via the fractional distillation of crude oil, also known as petroleum. As you know, petroleum is a finite fossil fuel formed over millions of years from the remains of ancient marine organisms under intense heat and pressure. Fractional distillation separates these hydrocarbons into fractions based on their boiling point. However, this process leaves us with an excess of large molecules and a shortage of smaller ones. To fix this imbalance, we use cracking to break large molecules into smaller, high-demand ones. Cracking of hydrocarbons can be performed at a large-scale commercial petroleum refinery or small-scale school laboratory. Cracking of hydrocarbons at the lab is designed to demonstrate the basic scientific principle of cracking using glassware, such as a test tube, a boiling point, and a delivering tube, rather than industry machinery. It specifically focuses on gathering a mixture of gases, alkenes, and alkanes, like ethene, by trapping them over water, which allows students to test the gas later. For example, using bromine water to check for unsaturation. Now, how do we demonstrate this process in a school laboratory? Take a close look at this classic exam image. This image shows a standard laboratory experimental setup used to demonstrate the catalytic cracking of long-chain hydrocarbons or liquid petroleum into smaller, more useful short-chain alkanes and alkenes. In the lab, we demonstrate thermal and catalytic cracking using standard apparatus. Let's look at the key components of the setup. On the left, we have a boiling tube held by a retort stand. Inside, the glass wool is soaked in liquid paraffin or crude oil to provide the long-chain hydrocarbon vapor when heated. A Bunsen burner heats the tube. The generated gas travels through a delivery tube and is collected in an inverted test tube. Looking at the collection method, what can you deduce about the physical properties of the gas mixture being collected? Correct, it must be insoluble in water. The collected gas is a mixture of short-chain alkanes and alkenes. These smaller alkanes are highly flammable and in high demand as fuels. Meanwhile, any hydrogen produced can be used to manufacture ammonia in the Haber process, or to harden vegetable oils into margarine. Let's zoom in on the missing level in this diagram. Starting with blank number 1. What should be written in blank number 1? It represents pieces of broken porous pot or unglazed ceramic. Can anyone tell me the chemical names of the two main compounds found in a porous pot that act as catalysts? Excellent. They're aluminium oxide, Al2O3, and silicon dioxide, SiO2. They act as the synthetic catalyst matrix. We use a finely divided catalyst because it provides a larger surface area to break the chemical bonds at lower temperatures, which significantly increases the rate of the chemical reaction. Moving further down the delivery tube, let's identify the final component. Now, let's identify blank number 2 and the final blank. Blank number 2 is our collected product. A mixture of short-chain alkanes and alkenes. The last blank at the bottom labels the drop of water. This specific setup teaches us a lot about the properties of these gases, which brings us to our next slide. As we observe, the gases mixture is collected over water. This technique is specifically called the downward displacement of water. Downward displacement of water. This method works because the alkanes and alkenes produced are highly soluble in water. True or false? The answer is false. For a gas to be collected via water displacement, it must be insoluble or only slightly soluble in water. Because hydrocarbons are nonpolar, they do not dissolve in water, making this collection method perfect. Expect to see this exact question in your paper 1 or paper 2 practical data questions. Now, we understand the setup. Let's formalize the exact reaction conditions required. To crack hydrocarbons successfully, you must memorize two industrial conditions. A high temperature of approximately 600 degrees Celsius and the presence of a finely divided catalyst like aluminum oxide or silicon dioxide. Breaking strong carbon-carbon and carbon-hydrogen covalent bonds require a massive amount of energy. Therefore, cracking is highly endothermic reaction. In our lab setup, the burner Bunsen supplies this thermal energy, while the catalyst allows the reaction to proceed efficiently at a lower activation energy. Let's look at a concrete chemical equation to see how a molecule actually splits. This is an example of cracking of decane. Decane C10H22 is a medium chain alkane found in petroleum. When decane undergoes catalytic cracking, it cracks into smaller alkane and short chain alkanes. For example, decane C10H22 produces butane C4H10, ethene C2H4, and butene C4H8. How can we chemically test the product to produce that an unsaturated alkene like butene was successfully formed? Spot on. We bubble the gas through aqueous bromine. If an alkene is present, the orange-brown bromine water will rapidly decolorize to become colorless. Alkanes will not do this in the dark. Take note that in the O-level exam, colorless is the required keyword. Colorless is the required keyword. Time to test your memory with a few past year question checkouts. Quick check 1. Here's your first retrieval question. State the name of the industrialized process used to manufacture alkanes from the long-chain alkanes found in crude oil. I will give you 3 seconds to think. 3, 2, 1. The answer is catalytic cracking. Or simply cracking. Well done if you got that right. Let's try another one regarding the product's form. Quick check 2. What chemical products are made during the cracking of long-chain hydrocarbons? Think carefully about the combination. 3, 2, 1. Cracking? Always use a mixture of shorter chain alkanes and alkenes, or short chain alkenes and hydrogen gas. Remember, you must always produce at least one unsaturated alkene product. Let's look at one final question focusing on the hydrogen gas byproduct. Quick Check 3. Final check. Name an industrial source of hydrogen gas used in the manufacture of ammonia via the Haber process. Three, two, one. The answer is the cracking of hydrocarbons from petroleum. This is a high-yield question that frequently bridges the air or ammonia chapter with organic chemistry in paper 1. While steam performing of methane, CH4, is a primary industrialized source of hydrogen globally, catalytic cracking of petroleum fractions is perfectly valid and expected as an organic chemistry crossover answer in Cambridge O-levels. Before moving on to a 2025 GCE O-level chemistry question, let's recap. What are made during cracking of hydrocarbons? The answer is short-chain alkanes and alkene, or a mixture of short-chain alkenes and hydrogen gas are made during cracking of long-chain hydrocarbon molecules. Let's review how the topic was tested in your recent national examinations. To wrap things up, let's look at how crucial this is for your exams. This exact concept was tested in the 2025 GCE O-level chemistry 6092 paper 2. Reactions involve hydrocarbon molecules of crude oil are shown. From left to right, hydrocarbon molecules to ethane, to ethanol, to ethanoic acid. This question presented a flowchart cracking hydrocarbons from crude oil and required students to identify cracking as the step generating small frame alkenes and a substance made through cracking other than alkenes. To identify cracking as the step generating small frame alkenes and a substance made through cracking other than alkenes. In conclusion, large long-chain alkanes are in low commercial demand and make poor fuel. Cracking is essential because it breaks these redundant large molecules down into shorter, highly flammable alkanes for fuels, and versatile alkenes and hydrogen for industrial synthesis. This is how we finally perfectly match consumer demand.